Waves. The time needed for a wave to make one complete cycle is it. Time needed. Hey, is that time period? Time period. Yeah, time period. You can measure that in seconds. Right? How much time in seconds to oscillate? Moro Josiah, Jordan. Sound. Example of a. Yeah. Oh, ooh, one winner. Yeah, sound is okay. Longitude. You guys see this poster over here? It says transverse versus longitudinal, right? So longitudinal is a compression wave. Right? That's what sound is. Right? Compression wave. That one's hard to draw if you draw little dots to represent air molecules, for example. Okay. Who got those points? Ooh, Emily. Yeah, says sound is a longitudinal wave. When two or more waves, same place, same time, the resulting effect is called. Uh, Interference. Right? You guys see a couple of posters over there. Got constructive, destructive interference patterns. Yeah, you could add their amplitudes, kind of thing. All right. Oh, Emily, top spot. Two Zacks with points. Where can you touch a standing wave on a rope without disturbing the wave? Hey, I think it's these nodal points right here. Node, node, node. Yeah, nodes. If it's a standing wave. All right, got Zach, Amora Josiah, Jordan, Emily on fire. Standing waves can be set up. Yeah, all those. Right. Now the red and the blue are longitudinal sound waves. The yellow one, if you pluck a string instrument, well, that's more like a transverse type wave. Yeah, those could all be types of standing waves. Right? Different categories of standing waves. Could all be. Bug jiggling up and down, swimming towards you at the same time. Compared to the frequency the bug is emitting waves, the frequency of the waves reaching you. Right here. The frequency. Yeah, it is a higher frequency. You guys know this Doppler effect? Doppler effect, right? So if the bug's jiggling up down like bloop, 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 but it's swimming towards you, those ripple waves are reaching you like bloop, 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 bloop. That's a higher frequency that the wave crests are reaching you, right? And then if it was like a sound wave, it'd be like a higher pitch. That's thank you. So same scenario compared to the speed that the bug is emitting waves, the speed of the wave reaching you. Just the wave speed. Yeah, the speed of the wave stays the same. Because once that wave has been released out into the world, it just like into some medium, it just goes whatever speed it goes through that particular medium, right? Regardless of the motion of the source or the observer, right? So the speed of those individual waves. That's why, if you look at that Doppler effect poster over there, it measures the graphic that was shown. Right? The wave crests are shown in like concentric circles. Well, I should just say circles, right? The fact that they're circular or in 3D space, they'd be like spheres, is evidence that maybe they travel like some speed through that medium, right? So the speed doesn't actually change, right? But the frequency of the crests could change depending on the motion of the source or the observer. Right? Zach, taking the top spot. The sound of a car's horn passes and recedes away from you. The pitch seems to decrease pitch. There's the Doppler shift right there. Lots of points. The Doppler effect is the change in observed frequency due to motion of the source for observer. Yeah. And in that Doppler effect equation, which is on the poster, there's a couple of plus or minuses, right? So you can figure, well, who's headed towards or away from what direction they're going to make a difference, right? All right, Emily, back with the top spot. If you double the frequency, what happens to the time period? Yeah, half, right? So time period, frequency, are reciprocals. So here's an example. If you heard like be 1 beat per second, right? So the time period would be 1 second. The frequency would be 1 hertz. Okay, okay. What if you heard like that's kind of close to 2 beats per second? I'll call that a frequency of 2 hertz. And then the time period between beats would be half of a second. Ah, reciprocals. All right. During a single time period, the distance traveled by a wave is one wavelength, right? So a wave will travel a distance of 1 wavelength in a time period, one time period, right? If you divide those two, right, 1 wavelength divided by 1 time period, you get the speed of the wave. Or you can also say 1 wavelength times the frequency, right, would be the speed of the wave. Right? I've got Jordan, Amora, Josiah, Zach, Emily on fire. Child swings back and forth on a playground swing. If he stands rather than sits, what happens to the time period? Yeah, the time period would decrease. Switch this over here. I'm just gonna throw up some notes from earlier today. Right, looks like this. Right, here's a couple kids on swings. The sitting kid, the standing kid. Right, and what's the physical difference? Well, maybe the effective length of the pendulum. Right, if you look at the center mass of the kid that's sitting, that's resulting in a long pendulum. Versus when he stands, the center mass moves up, and that shortens the length of the pendulum. Right, here's time period of a pendulum: 2 pi squared L over g. So if this L gets smaller, the time also gets smaller. It's a square root type relationship. So maybe the kid on the left is like swing, 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 and the kid on the right is probably like swing, 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 swing. It's going faster. It's a decreased time period. Swing. Suppose simple pendulum suspended in an elevator. When the elevator accelerates upward, what happens to the time period of the pendulum? Yeah, decrease. Why would it decrease over here? Right. The same thing. I'm just referring to this from earlier. Right? So you're staying in the elevator. Let's say the elevator is, maybe either at rest or otherwise not accelerating. Okay. You feel your normal weight. The pendulum swings back and forth, all fine and good. Time period equals 2 pi squared L over g. Okay. Right. Now let's have this thing accelerate upward. Guys, if it's accelerating upward, do you feel really light or really heavy inside? Yeah, really heavy, right? That floor is really being pushed into you. If you're standing on the scale, I bet that scale is reading like more than your usual weight. You feel really heavy. Okay? So it's like somebody turned up the gravity. Ooh. Okay. Now, if you want to do this the full proper way, I guess there's longer procedure, but you can do a little shortcut. Do you think you could effectively do something like this? Like G plus A here, right? Okay. So if it's accelerating up at like 3 meters per second squared, you get like 10 plus 3 down here, right? So increasing the denominator, does that make the overall fraction smaller? Which is like decreasing the time period. Yeah. So I think that makes sense too. Like in a regular elevator, if it's like, or if you're at rest, maybe it's like swing, swing, swing. Now this whole thing's accelerating upward. And it's like swing, 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 swing. Now it's going back and forth really fast. That's a decreased time period. Say an increased frequency. Swing. I got Jordan, Zach, Amor, Josiah, Emily. Observe around the ground. Here's a sonic boom that is created by an airplane flying at a speed. Yeah, where do you hear sonic booms? Yeah, greater than the speed of sound. So supersonic, super greater than sonic sound. Supersonic. Right. Yeah, you guys see that nice cone wave over there on the supersonic poster? Yeah. Right. It's cone wave 3D. A sound wave that has a higher frequency has a wavelength that is yeah, shorter. So we got speed equals wavelength times frequency. Now, um, suppose if you're listening to sound waves, right? So if I talk at a high pitch, that's a high frequency. If I talk at a low pitch, that's a low frequency. Right, guys, do those two pitches have the exact same speed? No. Yeah, the speed sounds the same. Right, it's the same, like about 340 meters per second from me to you. Right, but it's different frequencies, different wavelengths. Yeah, I've got an inverse relationship between frequency and wavelength. All right, speed equals wavelength times frequency. Two waves, same place, same time, same step. Each has an amplitude of 1 meter. What's the resulting amplitude? What is 1 meter plus 1 meter? 2 meters. So 1 plus 1 is 2. So just a constructive interference. Okay, constructive interference, 1 plus 1 is 2. Ooh, got points to Maura, Josiah, and Emily. Weight on the end of a spring bobs up and down 1 cycle every 2 seconds. What's the time period? Bob, 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 bob. Yeah, 2 seconds. 2 seconds time period. All right, all right. All right. Different question. Guys, what's the frequency of that motion? Half a hertz, right? Half a hertz. Right? So yeah, the time period would be 2 seconds. A leaf on a pond oscillates up and down 2 cycles every second. What's the as a wave passes? What's the frequency? Bob, 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 bob. Yeah, that's 2 cycles per second. Call that 2 hertz. And what would the time period be between bobs? About half a second. Huh? Right? I got Zach, Jordan, more Josiah, Emily. Wave travels 10 meters in 2 seconds. What's the wave velocity? Yeah, 5 meters per second. It's 10 meters per 2 seconds, 5 meters per second. All right. Now Logan hopping in, top 5. Emily, suddenly, oh, for the win, for the win. Wave has 2 crests, 2 troughs each second. The wave travels 120 meters in 3 seconds. What is its wavelength? Here, go over this with you guys. Guys, 2 crests, 2 troughs each second. That tells you it has 2 what? A frequency of 2 hertz. Is that a frequency of 2 hertz? Kind of like that leaf bobbing up and down, right? So this frequency is 2 hertz, 2 hertz, right? Guys, if it goes 120 meters in 3 seconds, what's the wave speed? 40 meters per second, right? 40 meters per second, right? So speed equals wavelength times frequency. Take 40 meters per second, divide by 2 hertz. It gives you wavelength lambda equals 20 meters. 20 meters. All right, you guys good there? Okay. Who's got any questions about those? Let's go to the podium with the bronze. Zach wants to believe the UFO silver. Amora Josiah. And go Emily. Runners up, Jordan and Logan. Nice job. Let's do sound. Sound time. All right, recording back here. Here we go. Paul Hugh. I got a couple of Paul Hugh demos for you guys. Yeah, physics. Oh, you guys hear it throbbing like that? Right. Does it sound like it's throbbing about pretty close to 1 cycle per second? Maybe not exactly. I'm rounding a little bit. Maybe 1 cycle per second. Could you call that 1 hertz? 1 hertz. Right. The fact that you're hearing about 1 hertz means that the difference in frequencies of those cheat tuning forks, guys, this is some of the questions you guys are about to see on Kahoot. The difference in frequencies is also 1 hertz. So for example, if this guy on the right was like 300 hertz, this guy on the left would be 301 hertz. Okay. Right. So you guys got that? Beats. Right. Oh, you know what? I got some other demos for you guys too. You guys want to hear a 340 hertz sine wave? 340 hertz. Now, guys, speed equals wavelength times frequency. The speed of sound is 340 meters per second. If I'm playing a frequency of 340 hertz, what would the wavelength be? 1 meter. 1 meter. Right. I'm about to send a sound wave into this room that has a wavelength of 1 meter. So if you could see the air molecules like crunched up, they'd be like 1 meter apart. What if I double the frequency? What's that going to sound like? What is double the frequency? Hey, it's 1 octave up. 1 octave up. All right, you guys ready to start this thing? All right, there's the pin on the board too. Okay, here we go. It's still recording. Sure, yeah. Oh. I have my sound turned off. Okay. Oh, we're not getting the Kahoot music right now. Okay. Compared to the speed of light, sound travels. Yeah, a million times slower. Speed of light's like 3 times 10 to the 8 meters per second. That's like 300 million meters per second. Speed of sound's like 300 something meters per second. Yeah. So million times difference, order magnitude. All right. Yeah, Zach, Emily, Jordan, Amor Josiah, Chub Bob Swordpet. Sound wave is longitudinal, right? Sound wave is longitudinal. It's like a compression wave. Sound wave is a compression wave. All right. Sound waves cannot travel in vacuum. There you go. Okay, so sound needs a medium to travel through. Now that's not necessarily true of lightweight. Light can travel through vacuum, right? So we get light from the sun. The sound needs a vacuum because sound's a pressure wave. Yeah. Well, Wiener in the top 5. Jordan, Amor Josiah, Zach, Shud Bob Soypant. On fire. Sound travels faster in the air if the air is. Help you out, right? So it says 331 meters per second at 0 degrees Celsius. And then every degree Celsius above that goes a little faster. Yeah, warmer. Right? Okay, so you guys were able to navigate that formula that flashed up there. That formula is not exact. That formula is showing a linear relationship. It's not exactly true, but it's a good approximation for about room temperature or thereabouts. All right. Yeah, a little faster through warm air than cold. Noise canceling earphones. Hey, we talked about this last week. Example of what? Yeah, destructive interference, right? So I was showing you guys transverse examples, but longitudinal you can do too, right? You just reverse all the high and low pressure points. That's a noise canceling headphones. Which of the following does sound travel the fastest? Ice looking for. So general rule of thumb, sound travels fastest through solids, and then second through liquids, and then slowest through gases. So, okay. Yeah, so for those options, solid ice is the fastest. Beat, 2 tuning forks. Yeah, have almost the same frequency. You guys remember before I started this Kahoot, I was playing that Paul Hewitt demo, where you had 2 tuning forks that were a little bit different, right? Yeah. And then all you do is subtract the 2 frequencies, that gives you the beat frequency. 1608 hertz tuning fork sounded at same time a piano note is struck. You hear 3 beats per second with 3 hertz. Which frequency, which could be the frequency of the piano string? Yeah, 2 possible correct answers. No, they said one of the frequencies was 1608 hertz. You strike that with something else and you hear a beat frequency, it sounds something like that's pretty close to 3 beats per second. That's what it would sound like. Right? So it could be either of those, because 1608 minus 1605 or 1611 minus 1608. Either one will get you there. Right? You guys get that? Beat frequency? Beat frequency. All right, Zach, racking up the points. An explosion occurs 1,000 meters away. Sound travels at about 340 meters per second. How much time to reach you? Yeah, pretty close to 3 seconds. Take 1,000 meters, divide by 340 meters per second, really close to 3 seconds. In fact, a good rule of thumb is if you ever see a lightning strike and you hear the thunder some number of seconds later, divide by 3. That'll show you the number of kilometers away that is. Right? So 1,000. Well, here, okay. Guys, got. Right. Usually here in the States, we're taught the divide by 5 rule for miles. So guys, let's see if you guys get this. Suppose there's a lightning strike, and then you count off 15 seconds, and then you hear the thunder, right? So there's a 15-second delay. How many kilometers away is that lightning strike? 5, right? Because 15 divided by 3 is 5, right? Let's turn that around and let's turn this up to American terms. So same scenario, 15-second delay. How many miles away is that lightning strike? 3 miles is divided by 5, right? Hey, 3 miles and 5 kilometers. Is that almost exactly the same distance? Yeah, that's almost exactly the same distance. Here. All right, more to side, moving up. And Zach, Chuck Bob Serpent in the lead. General rule for estimating distance in kilometers between observed results, count the number of seconds between the lightning and the thunder, and divide by. So we're going for kilometers, right? Kilometers. That is some thunder. Thunder time. Yeah, divide by 3, right? Comes from speed of sound. All right. If you pick the green one, you're probably thinking in terms of miles. All right, we got Jordan, Emily, Amor Josiah, Zach, Chubb Bob Serpent. Compared to 10 decibels, 50 decibels is what? Here's a hint. We're talking about log scales, so you could call that exponents. It's the flip side of that. Logarithms, exponents. Probably talking about many orders of magnitude. Ooh, one winner. Here, walk you guys through this. You guys see that prefix deci? What does deci mean? We almost never use that in this class. What is deci? It's yes, 1/10, right? 1/10. So 10 decibels. Can I just call it 1 bell? Is that okay? And 50 decibels. How many bells is that? 5, right? So we got 1 bell versus 5 bells. Is that okay? Now the intensity is 10 to the power, 10 to the power of the number of bells. Guys, what's 10 to the power of 1? 10. What is 10 to the power of 5? Is that, what is 10 to the power of 5? Is that 100,000? 100,000? Okay, now let's divide this two. What is 100,000 units here? Divide by 10 units here. 10,000 times the intensity. In the unit would be watt per square meter. So like, it's 10,000 times the number of watt per square meter. That's what intensity is measured in. Ooh, Chud Bob Swordpet. Extending the lead.
Interruption. At this time, we are in a shelter in place for inclement weather. I repeat, the shelter for inclement weather. Please keep students indoors at all times and stay tuned for further updates.
All right, lightning storm. So you count a 5-second delay between the lightning and the thunder. How far away in meters? All right, nice. All right, so equivalent answers could be 1.7 kilometers or approximately 1 mile. Right, those are all pretty close to equivalent distances. Right, 1 mile. It's actually about 16 something kilometers, but. All right. Emily moving up. Zach, Chud Bob, short in the lead. 680 hertz sound wave travels at 340 meters per second with a wavelength of speed equals wavelength times frequency. 340 meters per second plus how many meters times 680 hertz? What is 340 divided by 680? It's that many meters. Yeah, half a meter. Where's my demo of this? Hey, you guys want to hear 680 hertz again? They said 680 hertz, right? Here's 680 hertz. Hey. Right. That has a wavelength of half a meter. There you go. More Josiah, moving up. Zach and Chub Bob Sorpet. Beats. Urban, 2 tuning forks, 244 hertz and 250 hertz are sounded together. What's the beat frequency? 6 beats per second. Just subtract the 2 frequencies, get 6 hertz. All right. Points. Oh, 10,000 exactly to Chud Bob Sorpet. How many times per minute will you be in step with a friend when you're walking? See, 79 steps per minute, and your friend's walking 70 steps per minute. Hey, steps per minute. Just sound like cycles per unit time, like hertz. Ooh. Yeah, 9 times per minute. It's 79 minus 70. That's how you get there. 79 minus 70. Right. So if you follow those two guys with the camera, you're watching side by side, frame by frame by frame. Suppose you have like thousands of frames, right? And yeah, 9 times per minute. It would be exactly in the like same, like both left their right foot forward, something like that. All right, Zach getting points. sound a tuning fork. Same time you strike 1060 hertz note on a piano, you hear 2 beats per second. You tighten the piano string very slightly, now you hear 3 beats per second. What was the frequency of that tuning fork? Here, help you guys out here. Let's do guess and chat. Let's guess 1058 hertz. Guys, what is 1060 minus 1058? That would be 2 beats per second. Okay, so we're good so far. Then you tighten the piano string to 1061 hertz. Guys, what's 1061 minus 1058? That'd be 3, which would give you 3 beats per second. Oh, I think that one actually worked. I think that one worked. Yeah, 1058 hertz. I think that 1058 hertz. Well, yeah. All right. And you can check in, but you cannot leave now. Ha ha ha. You're sheltered in Griffin's place. A sound wave travel, it's got wavelength 0.5 meters and room temperature, has a frequency of about speed equals wavelength and frequency. What is 340 meters per second divided by 0.5 meters wavelength? What is 340 divided by 0.5? The 680 hertz. Hey, 680 hertz. 680 hertz. There's the answer. Oh yeah, 680 hertz. All right, more points. Oceanic depth sounding vessel surveys the ocean bottom with, okay, sound travels 1530 meters per second seawater. And there's a 12-second time delay to hear the echo. Right back. What's the ocean depth? All right, I'll walk you guys through this one too. Guys, if it's a 12-second round trip, then what's the one-way trip all the way to the bottom? How much time? 6 seconds? So 6 seconds down and 6 seconds back. Now let's do distance equals speed times time. What is 1530 meters per second times 6 seconds? Yeah, 9,000 and something meters. Yeah, over 9,000 meters. Right? 1530 times 6. You guys get that? Distance equals speed times time. Right? So one-way trip was 6 seconds. All right, we got them points. Amor Josiah, getting points. When an object is forced to vibrate at its natural frequency, resonance occurs. Truth, yeah. Hey, you guys remember Chase from California with the wine glass? Broke the wine glass? Yeah, that was resonance. You guys remember his parrots in the back? For the win! Even a steel bridge can collapse because of resonance. True or false? True. Yeah, you guys remember Tacoma Narrows Bridge? Tacoma Narrows Bridge? Tacoma Narrows. All right. To the podium. Podium. With the bronze. Zach wants to plead with the silver. Amor Josiah. And the gold. Quebec. Runners up. Jordan and Italy. Nice job. All right. Way to go. Kahoot winners. All right, let's see how we're doing on ooh, whoops. Oh, my screen freeze. Let's pause this here. All right, that's where we are.